Today, with reinforcement learning, this is where things are going to start getting interesting, because we will be moving from a world where someone tells us what to do with imitation learning to a world where the agents interact themselves to figure out exactly how to learn policies through trial and error. To recap where we left off, in imitation learning, we had an expert give us demonstrations, some data set with state action trajectories, and our goal was to find and learn a policy that mimics or copies this expert. And so we had this example with self-driving cars where, we observe the road, we pass it through our policy, and then we get some steering decision, for example. But the fundamental question or limitation here is that we are entirely dependent on the expert, on the quality of the demonstrations that the expert provides. And imitation learning fundamentally doesn't have a notion of being better than the expert. We can never become better than this expert trajectory data set that some unknown expert collected. And so this is essentially the ceiling we're trying to break today with reinforcement learning. Before we get into this, kind of like a quick recap for the MDP formulation, the Markov decision problem, since this is what RL essentially builds upon. So we have, again, this state space, the action space, transition dynamics, and a reward function. And this essentially loops this environment agent interaction. So the robot observes some state, and then it selects. We will do questions later, sorry. Selects an action, and then we will get a transition together with the reward of this. We also defined that we are optimizing in MDPs. Is not working? Oh, again? Can you hear me now? Is this better? Sorry, what? Can you hear me better? Yes. Okay, perfect. All right, thanks for the tip. So we mentioned the accumulated return is the reward the agent receives. Trying to get this. All right. And the RL objective is the expected return under the trajectory distribution induced by our policy. And so the optimal policy is the argmax of J over here. And so last time we didn't fully answer how are we actually computing now this policy, and that's what kind of the agenda is for today. Maybe before we start talking about RL algorithms, I guess kind of like a funny question. So imagine we want to train this RL algorithm, and we have this toy example, right, where we are driving through the mountains on this narrow road, and we have, let's say, a reward of +1 for staying on the road, and a reward of -1 for the car falling off the cliff, right? And now, in principle, there appears to be some sort of discontinuity here in this between staying and falling on the road, right? And if we try to directly optimize this reward function, let's say with the state of the car or something, then we can't really solve this directly with our favorite gradient descent solver, because it's a non-smooth function, right? So it's not continuous and it's not differentiable. And as you can see here, it's essentially like a Heaviside step function. And so the gradient is essentially 0 everywhere, except so you don't get any learning signal for this, except at the boundary where you jump from -1 to +1, where it's undefined. And so why can we still learn these behaviors, even if this reward function is like not differentiable, right? And so ultimately in RL, like it's all about maximizing expectations. So in principle, we often talk about like, actions that get high rewards in, like discrete actions or so, but we are typically interested in optimizing the expected value of those rewards. And here the magic lies in the fact that the expected values can be perfectly continuous in the parameter space of their distributions, even if the underlying reward function is highly discontinuous. And so this allows us then to use smooth optimization methods like gradient descent to optimize these objectives that seemingly are non-differentiable, such as like binary rewards for the car driving example. In our case, if we model, let's say, the event of falling from the road, kind of as a Bernoulli variable, then although we will have this sharp discontinuity, the expected value of this reward with respect to our policy parameters will remain smooth. And here is kind of the visual confirmation of everything I just said. So the red line is still kind of the original reward function, the non-smooth heavy step function with 0 gradients almost everywhere. And then the blue dashed line is the expected value, which is effectively a convolution of the reward function with the policy's density function. And so kind of the key message here is that marginalizing over a stochastic policy turns a non-smooth reward function into a smooth objective. All right, so we have now our objective. We have this expected discounted return, and we know now that it's smooth in policy parameters, and we can now try to train on this grade. And we know that this is essentially a scalar value that tells us how good our policy will be on average, starting from the first state. Right, so it summarizes the kind of entire quality of your policy in this one number. But there is kind of like one kind of practical issue when we try to do this, that it's essentially, if you look at this term, this means that we have to like expand this and unroll this to the end of the whole trajectory before we know how good we are doing, right? And this kind of like, is maybe not ideal for the car, because this means we would need to let the car fall down the cliff before we actually learn that this is like a bad thing to do. So this is essentially very slow and kind of like could be catastrophic in some cases, right? So what can we do about this, right? Is there a kind of a better way how we can go around this, right? Can we estimate this without unrolling each episode until the end? And the answer is yes, we can do this. And the key here is essentially the Markov property that we saw during the MDP lesson. Lecture that essentially we can factor the whole trajectory distribution without kind of like depending on the past to predict the future. So this leads us directly to value functions, right? So how, in order to avoid unrolling the whole trajectory before getting like the signal of what is good and bad. So the value function is kind of similar as the J scalar from before. It's again kind of like a single number that summarizes how good it is to be in a certain state. But now it is essentially now it's conditioned on the state rather than averaged over all the different starting states. So it's kind of like a local version that says how good is my policy from this specific state onwards. And the key idea of why we can use this value function is, again, the Markov property, that we can say that the whole future depends only on the current state and not on the full history. So while essentially conditioning on the current state is sufficient to summarize everything relevant about this, the past. And now, essentially, you can, I want to draw your attention to the last formula here that kind of explains the relationship between those two, where the RL objective is essentially the value function average over the different starting states. Okay, so how do we compute this efficiently? The insight for this is pretty simple. So any infinite sum of rewards can be split essentially into what we get right now in terms of rewards, and then like a discounted version of what we will be getting starting tomorrow. And so with this kind of like algebraic manipulation, we turn an infinite horizon problem into a one-step recursive equation. And this, going back to our car example, means that the value of being in a particular position on the mountain road equals the immediate reward I'm getting right now at this one step, plus some gamma times the value of wherever I will end up next. And so this means I don't need to simulate the full rest of my drive. I just need to know how good the next state is. And then the value function handles everything essentially beyond that. And this is what we call also like bootstrapping. So we only need to do this kind of one-step look ahead and then use our current estimate of V for the rest. All right, so now we have a way to evaluate how good a policy is. The value function we computed via the Bellman equation. But ultimately, we don't want to just evaluate a policy. We want to find the best one, right? We want to like improve the policy to find the optimal one. And so the optimal value function is simply the maximum value achievable from state S over all possible policies. So going back to the car example, the value is, the optimal value function is the value of being at a particular position on the mountain road when driven by the best possible driver. So it's essentially the best performance or ceiling any policy could achieve from that state onwards. And the optimal policy, on the other hand, is the one that achieves the ceiling or optimal performance from every starting state. And maybe like one insight looking into this formulas to make this tractable is that once we have the optimal value function, we don't need to search over all policies to act optimally. We just need like one greedy single step look ahead. So essentially, to summarize this, the key insight is that this optimal value function compresses this infinite horizon planning problem into a sequence of one-step greedy decisions. So all the kind of long-term reasoning or like anything about what will happen many steps into the future is implicitly encoded in this value function. So once we have computed this, we can like act optimally because it's like a kind of like a local computation. All right, so how do we actually compute the optimal value function in practice? Like the first answer to this is an algorithm called value iteration, which is surprisingly simple. We start by initializing all values to 0, assuming every state is worth nothing. And then we repeatedly apply the Bellman optimality update. Once we converge, we extract the optimal policy with one final greedy step. Like this is essentially, there is a conversion proof that because this is a contraction operation is bound to converge. Because essentially, when you apply this you apply the Bellman operator to two different value functions, you make them closer than before. But maybe like more importantly, like let's look at the limitations, right? So one big limitation is that this assumes that we have a known dynamics model, like a transition model in advance. So analytically, we also need to sweep through all the states. So it's quite heavy computationally, right? So for every state and every action, so which can become quite intractable for larger state spaces. And in practice, like we usually use like, some tabular representation for these policies. So like the state space should be like quite discrete and like quite small. So we can like enumerate it on a table. Here is a small example I programmed, or I let Claude program for me, not gonna lie. The setup is simple. The green cell is the goal with a reward of +1. The red cell over there is danger with -1. Then the gray cells are the walls. And the agent is stochastic. 80% of the time, it moves in the intended direction. 10%, the other times it drifts in like either direction. And so you can see here, like, what we just discussed. You start with total ignorance. And then once you start applying the Bellman updates, the states closer to the goal start updating. And you can see how it like kind of back propagates. So you can see how like visually the information flows through the state, backwards through the state space, one step at a time. And then the arrows you see are like kind of like the optimal actions for each state. So this is like dynamic programming in its purest form. No path planning. No, nothing hard-coded, just like repeated local Bellman updates. Okay, so value iteration works by taking the max over actions at every step. But this implicitly assumes we are acting optimally always, right? But maybe we want to also ask a simpler question first in terms of how good is a specific policy that I already have. And so this is policy evaluation. So it's very similar, if you look at this, to value iteration, except that we replace the max with expectation under the policy. So instead of picking the best action, we are averaging over whatever our policy tells us to take. So on its own, policy evaluation like doesn't improve anything, but it's kind of like the first step we need towards policy improvement, because you can't improve a policy if you don't know how good it is. And so this is essentially what we're gonna like look into next. Maybe just to clarify again before we move on to the policy iteration, I try to put both operations or updates side by side. So because it's easy to like conflate them, and they look essentially identical. But as I said, we change the max for like the expectation here. Maybe like on a side note, also because of this change also affects the complexity, because now we no longer maximize over all actions since the policy is fixed. So now it's going to be like state space squared. All right. And now we can put these two things together for policy iteration. So this is kind of our first way how we can improve our policies. We have our policy evaluation to measure how good our current policy is. And then we have a greedy policy improvement step from value iteration, which tells us how to do better given value function, right? And so here we are like essentially just alternating between both of them. Yeah, I just put the update rule for the policy evaluation, but this is kind of in reality a loop until convergence. I just didn't put it there. And yeah, so should be pretty self-explanatory. And this is also essentially guaranteed to converge because yeah, like the space of deterministic policies in this case is finite. And so each iteration should like strictly improve the policy until we have reached the optimal policy. So in practice, it converges pretty fast. Here is the same grid world example. And now you can see that we have like these two different phases between policy evaluation and policy improvement. And on the right, you see also the return plot, which should always kind of strictly go up. Because, yeah, as I said before, like every update should like strictly be better. Oops, sorry. Okay, so now we have a kind of a set of tools to for computing optimal policies, right? So value iteration and then policy iteration, or like with policy evaluation together, and they are beautiful and have like strong convergence guarantees. But there is kind of like a strong kind of limitation that makes them, or one of many, that makes them difficult to apply for robotics or kind of more complex problems. So essentially the biggest one is that we need to have a dynamics model at test time, right? So this means that this expectation requires marginalizing the value function over all transition distributions. And so for every candidate action we consider at every time step during the deployment on a real robot, we would need to like kind of calculate all of this. And so this would take like very, very long time to compute all this before actually executing an action. So for example, if we have like a high frequency robot, like it might be a little bit difficult. Right, and besides, in robotics, like it's often difficult to assume that we have a dynamics model because the world is messy and it's like sometimes hard to model. And as I said before, like even if you have a model, querying it at every time step might be slow, especially if you have like 7 degrees of freedom, like continuous action space for your manipulator. So you would need to evaluate infinitely many candidate actions. So, and this is kind of the fundamental motivation for Q functions. The key idea is, what if we could absorb the dynamics model into the value function itself during training, so that at test time, we never need to query this, right? And so during training now, the expectation over P is computed, and the result is stored in the over the dynamics model is computed, and then the result is stored inside the Q values. So this QSA already essentially contains or is baked in the answer to if I take the action A here, what's the best possible future return average over all the different ways the environment could respond. So the trade-off that we are making here with the Q functions is that it's slightly higher dimensional than the value function, right? So now it's not just conditioned on the state, but also on the action. But it might be more difficult a bit to learn because of that. But for model-free robotics, where we might not always have access to a reliable dynamics model, this is a price typically worth paying. This is just to reiterate the big benefit. If we actually do like Q value iteration at test time, we don't have to query the dynamics model. This is just a lookup or an argmax over a fixed function, so we don't need to simulate forward because the dynamics model is already encoded in the Q function itself. All right, so the Q function eliminates the need for the dynamics model at test time, but there is still kind of the problem that we need it during training time, right? And as I said, like we might even not always have access to a dynamics model. So how can we get rid of it entirely so we don't even need it during training? And so Q-learning, this is essentially where Q-learning comes from, and it has like a quite nice answer. We can replace the expectation over the dynamics model with a single sample from the actual experience. So we can, like essentially query the environment and kind of experience like what is happening. So we can, instead of calculate an average of all the possible future states, we just kind of take an action, observe a single sample, and store this transition. And we can create essentially this TD target, which is kind of like an unbiased estimate of the true Q value. And so we essentially now, with this learning update, we can nudge our TD targets towards the true Q functions by sampling from the environment, treating essentially the world kind of as its own simulator. Here is Q-learning running on the same grid world. And maybe you'll see kind of a difference from the previous examples, right? So in the previous examples, because we had this access to the dynamics model, like the policies would converge very fast, right? Now we don't have any dynamics model, and so we have to spend a long time kind of like exploring and querying like getting samples from the environment to figure out like what's the best policy. Right? And so I speed this up like quite a bit more than the previous demos to kind of show you. But this is, for example, one trade-off we are making. Now this is not as sample efficient as the previous algorithms that had access to a dynamics model. Okay, so we have Q-learning, which is a model-free algorithm that learns purely from experience. But maybe like I want to ask one question that is kind of subtle but kind of interesting, right? So we know that it learns from experience, but does it actually matter which policy collects the experience we use to update our Q values? So think about this carefully. Like, is there any dependency on like which?
No, because here we try to act with respect to the optimal policy already, so it doesn't matter which behavioral policy collected.
Yes, exactly. So as you very correctly said, the max operator is the key. It selects the best possible action at the next state, regardless of which policy generated this transition. And so this means Q-learning is off policy. And so the data that we use for the updates can come from any behavior. It can be a random agent, an old version of the policy, a human demonstrator, or any mixture of those. And that's what makes it also very, very powerful. The learning target always evaluates the optimal action independent of how the data was collected. So Q-learning is off policy because the max operator in the TD target always evaluates the optimal action, right? And here is also maybe like one variant of this for on policy, which is the SARSA algorithm, where instead of answering with the max, what is the best I could do next, we ask, what am I actually going to do next? So it learns the value of the policy it is currently executing, including all of its exploratory mistakes. So it's kind of like a very subtle change, right? Like it's essentially everything remains the same, except for this operation where we replace the max. And so this has like profound implications in the behavior that this will learn, this on policy, because the SARSA value, for example, if you have in the self-driving example, like a nervous driver, it will correctly penalize states where a nervous driver is more likely to do mistakes, while Q-learning will ignore this. Let's compare both in this kind of like classic cliff walking task, right? So where both agents start in the left and the goal is on the right, and there is like this kind of like death cells, right? And so you can see that the Q-learning finds the optimal policy, which is the shortest distance right across the edge of this like death cells, while the SARSA learns a much more safer policy where it's like not optimal, but it avoids going like on this ledge, so it doesn't like risk falling into one of these death cells. All right, so this is kind of like what we have seen so far. Right, so we have covered some exact solution methods like value iteration, policy iteration, and Q-value iteration, where you typically need a dynamics model, for sure for trading, for testing you don't need it for Q-values, and it's typically like for tabular representations. And then we have started looking into some value-based methods, where we start working with this like model-free algorithms that learn from interactions, but still kind of like constrained, right? In terms of like, okay, like very small state space and grid walls. Maybe like not super applicable for robotics just yet, right? And so now we kind of like think about how we can scale some of these things up, right? Especially for image observations, right? If we want to, maybe before we go all the way to robot arms, like play like video games, like, kind of Atari. Even then, if you want to have like an image observation space, this is like really, really big, right? It's like 256 pixels and then, values, and then like 84 by 84 pixels for the image. And then usually you need to like stack some frames so you can kind of see also what is happening before. So it's very, very large. And you cannot like store this, it's astronomically large, you cannot store this in kind of like a tabular fashion, right? And so this brings us to kind of like one of the seminal papers that kind of was a breakthrough in deep reinforcement RL, which is called DQN. Probably many of you have already heard of this. So this is deep Q learning. And the core idea is conceptually quite simple. You take everything you know about Q learning and replace the table or the tabular representation with a deep convolutional neural network. You input a stack of raw game frames, pixels, and then the output is like a vector of Q values, one per discrete action, and then you train it with your Q learning updates, and that's it. And why this is so seminal is that this was the first time where like a single algorithm with the same architecture and hyperparameters was able to learn all 49 different like Atari games directly from raw pixels with no like kind of like handcrafting or game specific engineers. Also, like as a side note, this was kind of the year I moved to Freiburg to study, where Martin Riedmüller was a professor, and he just left to do his sabbatical at a small startup called DeepMind. So that was like great times. So yeah, maybe I will skip this a little bit for time, but this is kind of the main algorithm we just covered. I want to go over 2 key innovations that they made in this paper to make this work. The first one is the experience replay buffer. The idea is simple. Instead of discarding each transition after using it only once, they stored it in a replay buffer and then sampled mini batches from this for training. Why was this important? Well, because it helps break temporal correlations, right? If you remember the whole IID thing in the first or second lecture we covered, right? If you inputted like consecutive transitions from the same trajectory, then this is bad for learning. In this way, they could break this temporal correlation and have these samples look approximately like IID to the optimizer, and then stabilizes the training. And also, you can then like also replay, of course, like past transitions several times, and maybe like there are like some interesting corner cases that then you don't have to like relive, that you can relive again. The second challenge here from using like deep networks for Q-learning comes from the correlation between the estimated value and the target value for the estimation. So concretely, the Bellman equation states that the current value the current value depends on the Q value of the next state and the current parametrization of the network. And so this means that an update for the current Q value will like essentially alter also the values for the next state, the next Q states, causing instability in learning and increase possibility of divergence. How they solve this is the trick is pretty simple. They maintain a separate copy of the network with frozen parameters to compute the target. This is why they call this delay target network. So typically, the second target network is updated either slowly via averaging or periodically after a number of fixed steps. Here are the results. I think the most important one is not just like the raw scores, but the generality that I mentioned before, that it was kind of the first algorithm that could kind of like out of the box without any hyperparameter tuning, like achieve like super, very, very good performance in this 47 games. DQN works remarkably well, but it has also kind of like a systematic failure mode, which is the overestimation bias. So the idea or the insight here is that like the Q values typically are not perfect. They have noise and errors, and the maximum of a set of noisy estimates is usually greater, or actually always greater, or equal to the maximum of the true values. And so here the noise doesn't get averaged out, but it gets amplified. And there was a later paper called double DQN that fixes this by using a very simple insight that the bias comes from using the same network to both pick the best value, the best action and evaluate it. And so then their idea was to decouple them using the online network to select the target network to select, and then the target network to evaluate. So you keep the same two networks from DQN, but you just like reroute them. Okay, now DQN works very beautifully for discrete action spaces. But in robotics, we are usually, because our robot manipulators and so on are continuous, we are interested in continuous action spaces, right? So this kind of now is kind of like a fundamental challenge of how do you apply this in robotics, because with this with the argmax over there, we cannot like enumerate like an infinite action space. Because there is no closed form solution for this kind of continuous optimization problem, there are like 3 different ways that we will very briefly discuss how we can solve them. The first one is discretization. So we can chop the continuous action space into a discrete grid and apply DQ indirectly. This is very simple, but it's exponentially costly in the dimensions. Like with a 7 degrees of freedom arm, even with a coarse discretization per joint, like this will explode combinatorially. The second one is sampling. So we could like also do like Monte Carlo sampling, draw like n candidate actions, and evaluate the Q function for each of the actions and return kind of the best. And the third one is to learn the argmax with a second neural network. That's going to be a DDPG. So instead of solving the optimization at test time, we try to move this into the training. So each approach is kind of different, but it tries to answer the same question, like how do you find the peak of a complex nonlinear function over a continuous space? And so the right choice also depends a little bit on your specific action dimensionality and setup and so on. Okay, so here here's one example for spatial discretization, which is kind of quite smart as it sidesteps this combinational explosion problem, where for pick and place, in this paper, they exploited the geometric structure of the problem by mapping the actions to the 2D top-down observations of the camera, so that instead of a separate action head, they use a fully convolutional neural network that takes kind of like a height map, so with RGBD, as input and outputs a dense Q value map, so 1 Q value per pixel, per rotation angle, and then evaluate this at 16 discrete orientations. So the argmax is over the map. And here is an example. Is this working? Yeah. Here is the system in action. The cool thing is that it doesn't like learn to reach or to grasp immediately. It actually first pushes objects that are cluttered to rearrange them into more graspable configurations, and only then attempts to grasp. So it first singulates and then grasps. And this pushing before grasping strategy was never programmed. Nobody told the robot that pushing is useful. So it kind of discovered this entirely on its own, purely from maximizing the reward signal. And this emerges through this Bellman backup, where the Q function for grasping assigns low value to cluttered configurations because grasping is the grasping success is low there. Okay, so spatial discretization works nice or beautifully when the action space has exploitable geometric structure. But what about the general case that we care more about when we have, like, let's say, a 7 degrees of freedom robot arm with like some joint configuration? The simplest approach is to use Monte Carlo sampling, right? So we sample n actions uniformly from the action space, evaluate a Q for each, and then return the best. And this works because the Q of pi is a smooth neural network function of A. And if we sample densely enough, we'll always find something close to the true argmax. So although it kind of works because it's smooth, as we said, it requires n forward passes per action selection. It doesn't really scale. And then also, like, the quality depends entirely on the number of samples and on luck. So there is no guarantee of finding like the right argmax. The cross-entropy method is a smarter version of the Monte Carlo sampling. So instead of sampling blindly from the entire action space, we iteratively concentrate samples around the high Q values. So the algorithm is pretty simple. We again sample some actions from a Gaussian, We then keep the, some number of elite actions with the highest Q, refit the Gaussian to those, repeat a bunch of times, and then return. And this works very, very beautifully. It has kind of two limitations. One, that it's a unimodal. So if it's you know, if like it has, if it will kind of like find the peak that you sample closest to. It's not like a guarantee for the true argmax. And then the optimization cost is paid at test time. So you have to like do like n times k forward passes at every single control step, right? So it really needs like a lot of time, or it can take a long time during optimization at test time. Here is an application of this paper called QT-opt. This was from Google and Berkeley. This is a demonstration of exactly this algorithm for robotics in a robotics farm. I think they had like around 7 KUKAs or so from 2018. And here, kind of, they made this work for the first time by using Q-learning with the cross-entropy method and a huge replay buffer of 580K real grasps from all these different robots, allowing each expensive, very expensive real-world transition to contribute to many gradient updates. Okay, so up until now, we've been using now this kind of cross-entropy method, right, to solve the argmax problem every time the robot needs to move. But as we said, like we have this n times k forward pass at test time. This is just like kind of inefficient, right? Especially like for high frequency control. Now, the third kind of like solution to this problem is DDPG, so deep deterministic policy gradients, that tries to learn the argmax instead of searching for it. So the idea is instead of sampling, we're going to introduce a second network called the actor, whose entire job is to predict, to directly predict the action that maximizes the Q function. So now at test time, we have collapsed this expensive iterative search into a single forward pass. And so now we have kind of these two networks, the critic, which is the standard Q network, like we saw in DQN. It's still being trained with the TD loss to estimate the value of state action pairs. And then we have the actor, which is the new part. We train this specifically to output actions that the critic says have a high value. So it takes a state and directly outputs a continuous action. Technically, we train, like how we train the actor puts us in policy gradient territory. We will cover probably this in the next lecture, so I will not go too much into the details for now. Think of this as just like the actor is trained to maximize the Q value, and gradient descent does the rest. Yes, maybe two small things before we finish. About how we update the actor. So we ask the critic in which direction the action space increases the Q values, and then we move the actor's parameter in that direction. Mathematically, we do this by applying the chain rule to the expected return, by taking the gradient of the Q function with respect to the action, and then evaluate it at the current actor's output and multiplied by the gradient of the actor with respect to its weights. And then maybe like one small issue is the exploration. So with DQN, we had discrete action spaces, but here our action space is now continuous, right? And so we can't do this greedy like with some probability we pick a random action. Like that would be actually bad because we could thrash our robot if we sample like random joint configurations. So instead of doing that in DDPG, we do what it does is it adds Gaussian noise directly to the actor's output at training time. So take whatever action it recommends and then perturb it a little bit with a slightly Gaussian noise to give you like smooth local exploration about the current actor's policy. All right, so here is how it looks like. There are also some applications for real robots of DDPG. It works now with high-dimensional observation outputs and continuous actions. We don't need cross-entropy method at test time. Maybe like one thing to note is that it's a notoriously brittle algorithm. It's very sensitive to hyperparameters and doesn't always converge. And as I said, this noise parameter needs to be tuned manually and for each new environment. And so if you pick it like too small, like you might not explore enough. And if you do a too large noise, then it's unstable. All right, to recap, here is kind of like a taxonomy and some trade-offs of the methods we discussed today. So starting from the left, we have the exact methods that are kind of clean and give you like convergence guarantees, but are restricted to having known dynamics model and working only on kind of like tabular environments or very small state space environments. Then we've moved to Q-learning and SARSA, to learning from experience rather from a known model. And we get convergence guarantees as long as we explore long enough. But we are still kind of stuck in kind of small toy environments. And then at the end, then we move to this, deep RL with discrete actions like DQN and double DQN. This is where things start getting interesting, where we have like our first neural networks. We can encode image observations. We get the replay buffer and so forth. But of course, we have now no guarantees for convergence anymore. And we are still stuck with discrete action spaces. And then finally, we've covered deep RL with continuous actions, with DDPG, QT-opt, and cross-entropy methods, which can now kind of handle continuous actions, high-dimensional state spaces, and we are still off policy with a replay buffer. With this, thank you for your attention, and yeah, let's move on to the papers.